All right, guys, we are live on YouTube. I was a little bit away. Yeah, I'm back. Can you hear me? All right,
Yes,
I can see Bryce. Sorry. I can see Jessica, Eugene, Dubem. Oh, we have Dubem here. That's not you. You're all guys welcome. So, sharing the link that we could share to our networks, and in 1 minute we'll be inviting Jesse to take the show. What? Can you say again?
no, I don't think he was talking to you. Please, Mr. Mbom, can you mute, please? Thank you.
Okay, you guys can hear me. Okay, that's fine. I think we are live on YouTube as well. So guys, we've been having a very great time this month. Couple of and kudos to you guys, and for some of the call to on the call, yeah, kudos. Let's invite our friends. Without wasting much time, just say we welcome you. We really appreciate you for you making out time to share a wealth of knowledge. So we want to learn more about the Huff language. You can take over and feel free to share your screen. Let me know if there's any issues.
All right, can you guys hear me?
Yes, you can.
Yeah, so good day, everyone. My name is Jesse, or Jessec on Twitter. I'm a blockchain developer, and I work. I think I got kicked out for some reason. Mr. Enoch, can you guys hear me?
Yes, we can hear you. Welcome back, Jesse. I think we're having some network difficulty because, okay, he's back.
Okay. Okay, yeah. I don't know if you guys got my intro part. I'll just take it back again. I'm Jesse. I'm a blockchain developer, and I work as a blockchain researcher for Rescues, and Rescues is a company that teaches like advanced blockchain stuff, both Solidity, zero knowledge, DeFi, and others are like so for like advanced engineers. And I will be walking through the Huff language, the basics of the Huff language for you guys. And is there anyone here who is a Solidity developer? Do we have Solidity developers here? Like you write smart contracts with Solidity. Okay, Mr. Hector. So anyone else? Yeah, so okay. Chimapa, yes, beginner. All right. So Huff is kind of like I'll just share my screen now.
Go and watch Disney Channel. Yeah. Good boy.
I hear you. Can you mute? Because we can
Okay,
hear you.
guys, please kindly mute. We just want the speaker to just be on. To be
Go and
on.
watch Disney
So can you guys see my screen?
Go and watch Disney Channel. One Disney Channel.
I think it's
Cinema.
this person.
What about
Can this person mute, please? It's Serachi. All right. So before I start, this is going to be a bit technical, right? Because at least you need to have some kind of like an understanding of how things work in the EVM and like a bit of like advanced knowledge of Solidity to be able to follow up fully, but it's still fine. Everyone is welcome. So that's why it's like an introduction to the language. So first, what is Huff? Yeah, so without wasting time, let's just start. Huff is an assembly-like language for the Ethereum virtual machine. So first, before I even go into the EVM part, notice the assembly-like language that I just said. If you are a Solidity developer, you must have written or at least heard about Yule or inline assembly, probably seen it in a code before, or you've written it yourself. So Yule is kind of like one level below Solidity. So Solidity is the higher level language for smart contracts, and um, the compiler, that's the Solidity compiler, does the job of doing the whole compilation from Solidity down to bytecode, and the bytecode gets executed on the Ethereum virtual machine. And then assembly is like one step lower, is a low level language, at least not as high as like Solidity. So you'll be the one to like manage your stack or memory, something like that. And it's kind of more complex than Solidity. So if you're familiar with assembly languages in other concept like in computer science as a whole, so if you've heard of assembly, so you know some languages, some static languages get compiled from the static language, you can compile it down to assembly, and from assembly down to like binary, or in the case of the EVM, bytecode. That's the yeah, so in case of EVM, bytecode, but in like normal computers, binary zeros and ones. So Huff is also an assembly language, but it's not like a general purpose assembly language. It's just specific for the Ethereum virtual machine. So basically the syntax looks like opcode. If you guys have come across Ethereum opcodes before, maybe through the documentation or something anywhere, so Huff looks exactly or almost like that with a little bit of syntactic sugar, like help you in developing. So, and notice here that I said for EVM. So I didn't say for Ethereum. One thing we should take note is that we must have had Ethereum compatible layer 2 or blockchain, something like that. So the reason why they are called Ethereum compatible is because programs or smart contracts in this case that runs on the Ethereum virtual machine or an Ethereum instead can also work in those blockchains. So examples like Polygon, Optimism, Avalanche, C-Chain, and the rest, Binance. So Solidity smart contract that you deploy on Ethereum, you can also deploy them on those EVM compatible chains. So that's why I didn't use Ethereum here specific, but EVM. This is just to say that Huff works both on Ethereum and every other EVM compatible blockchain, just like Solidity and you. And why was Huff made? Um, One reason Huff was made is to have like give developers greater control over their smart contracts. So imagine when writing a smart contract, the compilation process, some of you may not know, but we leave it for the Solidity compiler to handle. So the Solidity compiler does the job of like taking it from smart contracts in high level Solidity to bytecode, and then that bytecode gets deployed. So Solidity is not deployed on the blockchain; it's actually bytecode, and the compiler does the whole process of converting it from Solidity. So, but during this process, sometimes, not even sometimes, most times, the Solidity compiler do add unnecessary bytecode that may not be needed because it has to do like some safety checks, check if you are calling the right function, check if you are calling with the right amount of ether, and some checks. So basically, sometimes this check might not be necessary, or you might not even care about them. You might not care if they exist or not. And you can, if you had the option of saying, oh, don't implement this check, you can just go on, you do that. So this is where Huff comes in. So you basically write your bytecode yourself. But instead of writing like pure bytecode, although Huff is very similar to bytecode, so it's kind of like a mix of opcodes and bytecode. I'm not going to explain that. I'll just um, point you guys to a resource towards the end of the session that I can explain all of that for you guys. So that's why Huff was made. Um, to make devs have more control of their smart contracts and optimize your contract, implement stuff the way you like. Um, the Huff compiler does not add any extra bytecode for you like the Solidity compiler. So it's exactly what you implement, that's what you're going to get. If you implement A and A, you get exactly that. So there's nothing added, there's nothing subtracted or removed. Unlike the Solidity compiler, where sometimes it tries to do like some optimization, add some stuff or remove some stuff, and behind the scenes, you might not know. Although you get the same contract logic, but probably with like some extra sanity checks and the rest. And comparing Solidity to Yule and comparing Huff to Solidity and Yule. So Huff feels like bare metal in the sense that you are directly interacting with the EVM yourself. So you have greater access control, like you have greater control of your smart contracts. You are directly interacting with the EVM. You are implementing almost something that the EVM directly understands because the EVM does not understand high level Solidity, neither does it understand yield. So it understands only bytecode, the compiled bytecode. So when you write off, you're writing something very, very, very similar to bytecode. So it feels like bare metal because it's kind of more close and direct to EVM than Solidity or yield. And yeah, so more of less gas. So another important or something that the Huff language brings to the table is gas, like reducing gas consumption in smart contracts. And as we all know, smart contracts are one of, if not the major reason why Ethereum gas increases, like gas fee spikes up sometimes and come down, because transferring Ether does not take that much computational work. So most times transferring Ether has a fixed gas, just that the price might be higher, but the gas is like stable. So each amount of gas is actually priced, right? Because you might say, okay, transferring it, I think it takes around 21,000 and 2,100 gas, that's or 21,000 about. So if the gas price is high, that amount to transfer ether will be higher. If gas price is low, it's going to be cheaper. And one thing that impacts this gas price of Ethereum is smart contract, because the more the network gets like full, maybe due to a lot of transactions to smart contracts, the more gas increases. So it was implemented in one of the EIPs, EIP 1559, to like regulate gas in Ethereum. So the higher the computation in the network, the higher the gas fee. And then when everyone take like a pause, gas price reduces. So more Huff, less gas, because if most contracts are written in Huff and you write exactly what you want, you get exactly what you want. So no added bytecode, meaning no added gas. Because the reason smart contract interactions sometimes are costly is because of the amount of opcodes that are processed, or bytecode that are processed during the transactions, because this opcode and bytecode, they all cost like a certain amount of gas. So all of them accumulated can increase the amount of gas you pay for your transaction. So when we implement our contracts in bytecode or Huff in this case, we can avoid unnecessary added bytecode from Solidity compiler, thus making our code cheaper and gas efficient. So exactly what you want is what you write, and that's like more of like great control to Huff contracts. So brief history: how did Huff come about? The team behind Huff is the Aztec protocol team. So Aztec, if you don't know them, they are currently implementing a ZK blockchain, and they also have this language that they made, Neolang. So Neolang is like a language they use in writing, and you can use in writing ZK circuits, and it feels like has similar syntax to Rust. So it borrows like has inspirations from Rust. So Aztec is the people behind them, and behind this blockchain are the language. And then some years ago, and they wanted to create like an elliptic curve arithmetic library. So elliptic curve has to do with cryptography. And so they wanted to implement an elliptic curve arithmetic library on EVM. They tried using Solidity and Yule. It was very, very expensive, like in terms of gas, because since it's an elliptic curve and arithmetic library at the same time, there's a lot of computation, maths, and the rest of that. So performing those kind of stuff, although Solidity is Turing complete, meaning whatever it is that you imagine and you are able to implement, you can do it with Solidity, and it's going to work. And the only downside you have is just gas, because Ethereum blocks um, has a block gas limit. I think about 30 million right now. So if your smart contract, the computation in your smart contract is way, way intensive, your smart contract can get deployed, but you have challenges running them. So this is something similar the Aztec protocol faced when they wanted to implement their elliptic curve library in Solidity. So they went from doing it in Solidity, it was very expensive. They went down to Yule, which is like assembly too. So Yule is also like assembly language in like EVM smart contract. So it was also still expensive, and they had to implement their own language. This was how Huff um, came came about. So they did Huff. Over the time, Huff syntax has slightly changed from what they wrote then a bit. The compiler was like rewritten in Rust, and I think the original version was in TypeScript or Python. I can't really remember. And then they rewrote it in Rust and made like some changes. So this is just to tell you how powerful Huff can be. And Yule is known to be very, very gas efficient. Like if you are familiar with Yule and inline assembly, um, writing a smart contract in Solidity and then translating it to you often like give a lot of gas benefits, like noticeable gas benefits in most cases, except probably you turn on the Solidity optimizer, increase the runs to like a large number and stuff. So then you can get comparable um, like gas usage between Solidity and you. But normally writing smart contract in Solidity and then implementing the same thing in you, there's usually like a noticeable gas difference. So imagine when something could not be implemented in Solidity and it could not be implemented in Yule too, but it could be implemented in Huff. This is just to show that Huff like provides a lot and a lot of like gas benefits in terms of like transactions and smart contract interaction. So that was how Huff came about. And yeah, you can visit https docs.huff.sh slash get started overview. So I'll just send it in the chat so that you guys can see that. Yep. Yep. So going into the syntax of what does Huff look like and what are the benefits or key features of Huff? So I've been talking about gas, how Huff help you save gas, feels close to the EVM, upcode and the rest, but what does it look like? So right now, what we are seeing on my screen is the Huff, and this is actually a smart contract, but a tiny one implemented in Huff. So with Huff, you can declare functions and events, and just like this, if you guys can see this. So you start with the define keyword. So you do hash sign, define, then function, add, and then you pass in your function parameters, if it's accepting anyone. And also take note of how the parameters have no name, like no name, just the data type. So unlike in Solidity, you do something like function add, then you do like Unity physics, Unity physics, like you put the parameter name, like you give it the name A, norm, B, whatever you want to give it. But in Huff, you just write Unity physics. Although you can also do this in Solidity, but which most people are not aware of, but you can do the same thing in Solidity and your code will compile. And just that you have to manually handle this variable like almost the same way that I'm doing it here, but with inline assembly because Solidity does not um, support Huff. So, but with inline assembly, but that's like a bit advanced. So usually you see guys like devs, when you write your functions, you put the parameter name and the parameter data type. But this one does not have any parameter name, just data type. And then we are saying something new, non-payable. So in Solidity, there's no non-payable keyword, but there's a payable keyword. So if you are familiar with payable, you know payable is just to indicate that this function will have the ability to receive ether. That's like when you are calling the function, you can call it together with ether and like in the transaction, and it's going to like go through. And but in this case, we are putting like non-payable, but this keyword does not exist in Solidity. So how Solidity handles non-payable functions is that behind the scenes, you might not really know if you've not heard of it or learned about it or inspect your contracts. So every function in Solidity that does not have the payable keyword, the compiler adds some checks behind the scenes, like when your code gets compiled. This is an example of the bytecode I said gets added, and sometimes developers they don't know. So the compiler will add like some checks. So the check is just basically it's checking that you are not sending ether to that function since you didn't mark it payable. So for if you have like if you have a contract and you have 20 functions in all of them in the contract, so all those 20 functions, and if none of them are payable, like none of them have the payable keyword, the Solidity compiler is going to add this check. So you can just imagine the amount of bytecode that is going to be added to your smart contract. And you didn't tell it to add it, but you might not even be aware of something like that happening. But that's what the compiler actually does. So it's going to like prevent you from sending ether. That's why if you've ever used Remix before for like writing smart contract, probably when you are learning or when you are debugging or stuff, if you try to call a function that does not have the payable keyword and then you pass ether while you are calling the function, it's going to revert. Probably if you are using hard hat, foundry, remix, it will revert, sorry. So it's going to revert. The reason it's reverting is because of that added bytecode from the Solidity compiler. So it just add the bytecode to check that, oh, you can't call this function with ether since it was not marked payable. But in Huff, you have the option of saying payable or non-payable, view, pure. I think that's about it. There might be more, but you can mark your function as non-payable, payable, view, pure, or external public, like in Huff. But one thing we should know is that this definition, this function definition is more of like an interface ABI stuff. So it's not actually being added to the bytecode in the way like it does not work traditional, like the way traditional Solidity work. So if you define function in Solidity, after writing the function signature, that's like from here, Solidity does not have this defined keyword. So from here down to this part, it does not have non-payable too. You usually see like curly braces at the end, and then your function logic is going to be inside like the curly braces, but we don't have that here. So just brackets after returns, and that's it. So returns, there's nothing inside. This is to tell the Huff compiler that this function is not returning anything. But unlike Solidity, where you define your logic inside your function, you don't do that in Huff. This serves more like an ABI stuff, like an interface. You are familiar with like Solidity interface. So when you declare an interface, you don't define the logic of the interface, like the logic of the contract, because it's an interface. Interfaces are more like just like something like a document or a guide on how you are going to implement the main contract that is going to likely inherit the interface. So you can see this similar to an interface. So this is just the way to tell other developers and also the Huff compiler that I'll likely have this function and this event. And one major reason, although I'm not showing it here, but I'm going to show you guys when I get to code. One major reason you do this is because Huff has some built-in compiler that probably you want to get function selector. And I don't know if you guys are familiar with function selectors in smart contracts. So function selectors are just the kekak hash of the function name and its parameters. Yeah, so and then when you get the 32 bytes hash, you collect the first 4 bytes, and that's your function selector, sorry. So you can manually do that too in Huff, but it's way complex. So Huff has like some built-in functions to help you do that. So that's like one of the benefit of having support for function ABI definitions. So this is kind of like a static something. It does not really affect our code. And if you check here, the same thing with the event. If you check here, I added the comments below. The function and the event above is not used below. So the Huff contrast is still going to compile. This works fine. So it's the code to add two numbers, and the first number must be non-zero. And I implemented it without any functions, which is almost impossible in Solidity. You can't have logic that works like a function in Solidity without a function, but in Huff you can. So if you check here, you are not seeing anything like add, like the function add or the event added in this code section below. That's to say that I'm not actually using it. The reason I just put it here is just to show you guys. But by the time I go into the code aspects, we are going to see more about this. So Huff also supports constants, just like Solidity. So the one reason I think supporting constants is actually like a great idea is because it helps us reduce like a lot of gas, because since off is all about reducing gas, it makes sense, so much sense to support constants, because state variables, when they when we try to load state variable, like take for instance, you have a smart contract and you have a function in your smart contract that sets the updates a state variable, and then you have another function that retrieves the state variable and then like returns it, something like that. So the cost of loading a state variable is actually expensive. So it costs about 2,100 gas, so S load. To confirm that, there's this site called evm.code. So I'm just going to open it. Okay. Move this here. So evm.codes. And if we search for S load, okay, S load costs 100 gas. Sorry, I made a mistake. It's S store that costs 2,100. Where is that? This is for warm access, not code access. Yeah, so 2,300 gas. But there's this concept of code and warm access. So if you're accessing a state variable for the first time in your transaction, you are going to pay higher gas. But if you're accessing it twice, so the first one will be higher than the second one. So the first one is called a code access, and then the second access is called a warm access. So the warm access is actually 100 gas. That's why you see here S load said the minimum gas is 100. So this one is for warm access. Then I think cold access is about 2,100 gas. Uh, but if it's warm access, it's 100 gas. That's the first time you're accessing it in a transaction to cost you 2,100. But if you're accessing that same state variable the second time in that same transaction, it's going to be 100 gas. So this was implemented in a certain EIP on Ethereum some time ago. So, but by using constants, you don't pay for S load and S store, because in Solidity, constants gets stored in your bytecode, like at the end of your bytecode, and then the Solidity compiler will by itself implement logic to retrieve that constant from the bytecode whenever you need it. You don't manually do this, but it happens behind the scene. So Huff also supports constants, and I'll show you guys when I get into the code aspects. So Huff supports constants, and this helps minimizing like Earth like reading from storage, or since they are also constant, you are not actually paying to save them. They just get padded to the end of your bytecode. So you are not paying for S store, you are not paying for S load, even though you access them a million times in one transaction or multiple. You won't be paying. You pay for gas actually, because it takes gas to like get the constant from the end of the bytecode, but it's not as expensive as that of reading from storage. So constant are quite important in gas savings. So if you are writing a smart contract, just a general note, if you are writing a smart contract and you know you have a variable that you are not going to update, you just set it once. So it's always best to set it as a constant or an immutable variable in Solidity. And then next in line is jump labels. So Huff supports jump labels. So they are just like, you can think of it as a way to manage code execution or execution flow within a smart contract. This is in Solidity too, but like I said earlier, you don't do that yourself. The Solidity compiler handles it. But in Huff, you have to do it yourself. Since you're writing the bytecode, you have to do it yourself. So what these jump labels they help you do, they help you set the program counter. So if you are familiar with virtual machines and in computer science, so there's this concept of registers, program counters, and other types of registers. So program counters, what they do is that if your bytecode is executing, like you make a transaction to a smart contract, and smart contract is being executed as bytecode on the EVM. So the program counter tells the EVM what part of the bytecode is currently being executed, like what part of the bytecode, which opcode in your bytecode is being executed at that time. And with the help of jump labels, you can move this program counter through something called jumps. There are two types of jumps in the EVM. Um, there's the jump opcode and then the jump if. So if we go here and I search for, so by the way, this is evm.codes. Let me just paste it there, just in case you want to open it. So evm.codes, you see list of Ethereum opcodes. So these opcodes are basically what run our smart contracts. Our smart contract gets compiled to this in the form of bytecode. So if we search for jump, so what jump does, according to this definition here, the program counter, what I was just talking about, is a byte offset in the deployed code. It indicates which instruction will be executed next, blah, blah, blah. The jump instruction alters the program counter, thus breaking the linear path of the execution to another point in the deployed code. It is used to implement functionalities like functions. So what they are basically saying here is that the jump opcode changes the program counter. Um, since program counter tells the EVM which part of your bytecode is being executed at the moment. With the help of jumps, you can change your program counter from year to year. You can like jump around your opcode. Solidity does this. Solidity compiler does this for us when we compile our smart contract. We don't do it, but in Huff, you have to do it yourself. So Huff has this concept of jump labels, and how jump labels are defined is like this. So I like to name things in a descriptive way. That's why I named it reverse label, but it could be anything um, as long as it's not a reserved keyword. And so it could be revert label jump, it could be my jump, it could be our jump, anything. So it does not have to be revert label. Yeah. And so what this jump label does is that if you look closely, I am jumping to reverse label on this line 9. But let me just quickly explain the code. So first thing we do is that I try to get the first number we are trying to add, and then I duplicate the number, and then I use this opcode to check if the number is 0. If it's 0, because check the comment here, I said first number must be non-zero. That's like my own logic. So I said, if this first number is 0, jump to this revert label and then revert. So the transaction is going to be cancelled. So when you interact with smart contract and you see something like this transaction reverted, sometimes it could be reverted due to out of gas, like some stuff like that. But sometimes too, it might be reverted due to like some internal um, contract like port or something. And this reverse opcode is what handles that reversion. So when this reverse opcode gets hit, your transaction is going to revert, your smart contract will revert, and everything will stop. So yeah, but the reverse opcode takes two parameters: the offset in memory you want to revert from, and then the amount of data you want to extract from that offset in memory. So if I search for reverts here, so you can see it's offset and size. So hot execution, reverting state changes, but returning data and remaining gas. So it's going to stop your smart contract execution and then return data. So how it gets this data is by the memory offset you provide and then the size in that offset. So the example they gave here, they provided memory offset 0, and in memory offset 0 we have 2 bytes there. So FF and 01. 2 hexadecimal is 1 byte. 2 hexadecimal is 1 byte. So 4 is 2 bytes. Like 4 characters is 2 bytes. So it's going to revert with from offset 0, 2 bytes, and in offset 0, there are 2 bytes here. So this is the return data you get. But in my Huff example here, I just put 00 revert. So it's going to revert from offset 0, but with 0 return data, because why not? So yeah, so with the help of jump labels, we can move our program counter around. So basically, at this point, the program counter is going to be at is 0, and that's checking if the first number you are calling, you are trying to add is 0. If is 0 returns 1, I'll push reverse label onto the stack and then jump if. So this jump I or jump if is a conditional jump, more like an if statement. So what it does is that it checks if the item in this second layer of the stack is non-zero. That's if it's 1 or non-zero, 1, 2, 100, whatever. If it's non-zero, it's going to jump to the offset you put. So this revert label here is a jump offset. So Huff helps us abstract that by just putting creating a revert label like this, putting colon sign, and then the logic you want to happen whenever that revert label gets hit. So yeah, the next line is macros and functions. So macros work the way we expect functions to work in Huff. Coming from Solidity, you write Huff, and then your Huff, sorry, coming from Solidity, you write functions, and then your functions, you put in your desired logic, and when that function gets called, that logic gets executed. This is how macros kind of work similarly, although you don't call macros, so you can't call macro main. This macro name is main, and how we define macro, we just do hash define macro, and this macro keyword here is important, and then the macro name. So if you look closely, it's in capital letter. This is just a convention for defining macro, just like differentiate them from functions. So you can also use small letter, but it's bad practice. I think so. But it's bad practice. You should always define your macro in capital letter. And so the macro, after defining your macro, define macro main, and you put in your brackets equal, and then you put this takes and what it takes from the stack, returns what it returns to the stack. So if you are familiar with the EVM and how it works, the EVM has like stack and memory. So memory is where dynamic data usually are stored, but anything can be stored in memory. You can move stack items down to down to memory and take items from memory to the stack, as long as it's no more than 32 bytes, because the stack can only hold 32 bytes word. And yeah, so macros has the ability to take something from the stack. So I can define a second macro below here, for instance, and I'll show you guys an example in the code. I have the code prepared already. So I can define a second macro, and then from my main macro, or instead, from my main macro at this point. So instead of returning here, I will just leave something at the top of the stack. Okay, probably at this point. So when I do, I load the second number we are trying to add. Yeah, I'm loading the first number with 0x00 core data load and 0x20 core data load. So what this just means is that if you are familiar with the concept of core data, where you make a call, like an external call to a function in Solidity. So the function name and the parameters are what makes up your core data. That's the smart contract function that you are calling, and the parameters of that function makes up your core data, but not exactly the function name, but its selector. So it's not like you see a function add in your core data, no, but the selector, and the selector is just the hash of this with the parameter and then the first 4 bytes. So that's what makes up your core data. So the function selector and then the parameters of your function. So what core data load does is that it will load starting from the specified offset of your core data. So in this case, 0x00. So it's going to load the first 32 byte of your core data. But yeah, we are not using function, and we'll see how we can use function later, but we are not using function here. I'm just directly loading core data. So there's no, the add function is not being used here. So that's to say, the function selector of add is not part of our core data. Only the two parameters we are trying to add that are part of our core data. So 0x00 core data load is going to load the first number that I'm trying to add. Then 0x20. So 20 is just hexadecimal for 32. So to confirm that, I've just open chisel and show you guys. I don't know if this is wide enough. So 0x20 is 32. So 20 is just like 0x20 is just the hexadecimal representation of 32. And remember, I said earlier that each item on the stack are represented in 32 bytes. So our first number that we're going to add, let's say it was 1, is going to be represented like this on the EVM and in our core data. It's going to be implemented like this. So zeros will be padded to it just to make up for 32 bytes. So when you call a smart contract, um, the parameters you pass, if they are not up to 32 bytes, they get padded until they become 32 bytes. Although nothing is changed, just the padding. So if it's like 20, 20, 20, 20, it gets padded. The reason you are seeing this different number from this 2020 is because it's being converted to hex. If I convert it back to decimal, you see that we get the same number. So EVM does not understand pure numbers and pure strings or pure data. So only this hex, and everything gets converted to hex. So the first number will be loaded from offset 0 in our core data. And let's say it was 1, that's we are going to get 1 like this. And I wrote a code, a Huff code explaining that. So I'll just go here. So yeah, this is it. So this is same thing from the image. Define function, add events added, macro main, blah blah blah. But this one has comments. I didn't add these comments here because it made the image too large, and I didn't want to like zoom in or compress it. So this is what is happening behind the scene. So when I put 00 here, first, just you can imagine these comments at the side to be the stack. That's the stack of your EVM. Like when you make a transaction, a new EVM instance is going to be spun off for you. And remember, I said EVM has both the stack and the memory. So this is going to, just imagine this to be your stack. Yeah. So when I put 0x00, same as this, 0 is going to be pushed to the top of the stack. And then when I do core data load, it's going to load num1. That's the first number we want to add. And then we are checking that the first number is non-zero. Then when I do dup1, so dup1 is an opcode to duplicate an item on the stack. So the first item on the stack, there's dup1, there's dup2, up to dup16. And yeah, so dup1 will duplicate the first number on the stack. Then is 0. We check if the item at the top of the stack is equal to 0. So this is going to return a boolean that's 1 or 0, yes or no. And like I said, EVM does not understand yes, no, or hi, hello. everything gets converted to like hex. So 1 in hex, like I showed here, 1 in hex is 0x000, like it's actually 0x01, but it gets padded in the EVM, so that's why it's long like this. So 1 is 0x01, and yeah, so instead of it returning true here, it's going to return 1. So 1 is like true on the EVM, and 0 means false. So it's going to return is num equal to 0. If num is equal to 0, it will return 1. If it's not equal to 0, it will return 0 here. So we can either have 1 or 0 in this place. And then we still have num1 because I duplicated it here. And after that, next revert label. So it's going to push this revert label. This revert label will be given a number by the Huff compiler. So it won't still be revert label. It will be replaced with a number. That's a jump label number. So revert label is going to be our if statement, like is number 0, and then the original one that I duplicated, and then if is 0, jump to this place. That's what we are going to do. So when this jump if opcode gets executed, we only have num1 there. But if it's not 0, the jump won't occur. And then these two items will be pop off the stack. And this jump, if I hover on it, I have an extension that helps me explain what it does. So ASN, that's assembly, jump if or jump E, jump I. So it takes in an EVM PC, that's program counter, and then a condition that's true or false. So conditionally alter the program counter. So it pops off two items of the stack. So these two will be out, and then we'll be left with only num1, and that's what we have there. And then in this line, I'm loading num2. So when I do 0x20, 0x20, which is 32 bytes, sorry, not 32 bytes, which is 32, will be pushed to the stack, and then we still have num1 from before. And then core data load. Remember, I said core data load gets input data of current environment. That's your core data. So and it takes the data offset, and then the data offset I'm specifying here is the 32, starting from 32 bytes offset. So that's because, like I showed here, each items are represented as 32 bytes on the EVM. So if I had one would be like this, and if I had two, so imagine when I now have 1 and 2 together, I'm trying to add 1 and 2 together. So we are going to have something like 1 and 2 as our core data, although this 0x won't be here, but something like that. We are going to have like, let me just, so this is what our core data is going to look like this. So it's going to look like this, offset 0 down to the first 32 bytes. And then we start with offset 32, because since it's counting from 0, it's going to be 0 to 29. Yeah, 0 to 29 to this point here. And then this will be 32 to 64. That's another 32 byte. So by doing 0x20, that's 32 core data load, is going to load 2 for us. And then what we get here would be 2. And then I call the add opcode. If I hover on it again, addition operation. So add opcode takes A and B and then returns the result of the addition on top of the stack. It costs 3 gas, so it's not expensive that much. So we add num2 and num1. So one thing you should note here is how I'm implementing all of this myself. So unlike in Solidity, you just have to like have a function add blah 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 that takes in A, B, and returns A plus B for you, and that's it. But in Huff, you have to manually do that. So that's why they said you have greater control. Although the downside is that you have to write, it kind of like takes more time But that's not bad if you are looking for enough gas optimization. And then after getting our addition results, it will be placed on the stack. So I just put it in bracket to indicate that it's going to be the result of adding num2 and num1. And after that, I push 0 to the top of the stack. So we have 0, we have num2 plus 1, and then we store 0. We store the results at memory offset 0. So remember I said EVM has both the stack and memory. So stack is not addressable like memory. So stack does not have offset 0, offset 1, offset 2, offset 3. It does not have it. The only thing you use in moving around, you don't even move around the stack. You can only move around your bytecode with jump labels, but not around the stack. You can't reset the stack, but you can move around your bytes to like kind of like change the program counter. But memory is addressable. You can pick a particular place in memory and then store something there. And memory is temporary, so is stack too. So we are storing the results of our addition, adding num1 and num2 to memory offset 0. So this is going to leave the stack empty because mstore is the opcode. If I hover on it, you see save word to memory. And yeah, so it will pop off this two stuff. So the addition, it will take the addition result and store it as at offset 0. And then now memory is going to have this addition result at offset 0. And then the stack will be empty. The reason we are doing that is that we are trying to call the return opcode on the EVM. So the return opcode takes two parameters: the memory offset you want to return from, and then the amount of data that is in bytes you want to return. So hence we have to store our results first in memory before calling return opcode. So return opcode, if I hover on it, it takes offset and size. So this is the offset 0. Same with this one. We're storing at offset 0. Then this is the size, 32 or 0x20 in hex format. Recall I said um, everything in the VM is stored as 32 bytes. So the addition result, even though 2 plus 1, as I was using with this example, is 3. So what will be stored instead will be this. So 0x000003 added to 32 bytes. So that's why I have to put 32 here, or in hex 20, 0x20, and then I will return it. At this point, the transaction will halt, because if I hover on this hot execution, returning output data, so the return opcode stops your transaction, and once it gets hit, so your transaction pause and execution stops, and then it will return um, whatever offsets and data that you've specified there for you. So this is like great control of how your smart contracts work. You have to do that. So we do this stuff in macro and all of that. So Huff also has built-in functions and specialized functions. Example is the func. I'm not using it here, but it's here, and I'll get to this later or soon. So the func helps us get function signature selector and pushes it to the stack. I'm using it here to get the function selector of this one, and I'll get to that later. And there are other inbuilt function or built-in functions. There's the error that helps us get error selectors. If you've written custom error in Solidity before, and those custom error, they actually have like error selectors, just like function selectors. That's how the EVM knows. Like when you do something like you revert with the custom error, the EVM uses the error selector like to revert behind the scenes. You as a Solidity developer writing Solidity, you might not know, but when your contract gets compiled, the Solidity compiler does the whole process for you, and then your error selector, that's what is used when you revert with a custom error. So Huff also has not just the error built-in function or the func stick. It also has I think it has table stats. It has write pad to like pad data with zeros and stuff like that. So it has several other built-in functions that you can use. So one of the reasons of these built-in functions is just to help devs. So instead of you manually doing all of that, you just have to call the built-in function and it will handle that for you. If I wanted to get a function selector of this one, I can do that manually, but I have to start doing keka hash, blah, blah, blah in my macro, and that will add extra code or overhead for me. But with the help of built-in functions, that's the func in particular, I just have to call it with the name of my function, and it brings it up for me and keeps it on top of the stack, and we are good to go. So this is the key features of Huff. There are other stuff, and macros are reusable. If you've written Rust before, you see that Rust has macros, and macros help you achieve stuff like they are basically like a reusable code. So you can define one thing somewhere and then export it as a macro, and you can reuse it. So wherever you put the macro, the code you define in the macro originally just gets generated here during compile time. So and I'm using it here. I'll explain that soon. So what are some cool stuff that has been built with Huff? So first is there are several others that are not listed here. There are many, but one is HuffMate. So if I open this, HuffMate is like a library for Huff contracts, just like Open Zeppelin. You can import Open Zeppelin contracts and inherit it in the ERC20 token 721 transaction, payment splitter. I think that one is deprecated now and stuff like that. So HuffMate is exactly that, but in Huff. So if you come to tokens, so you see ERC20.Huff 11546267121. So this is ERC20 token in Huff. So yeah, there's 4626, there's 721 NFTs, 115, blah blah blah, and others. So this HuffMate is just similar to that of like Open Zeppelin contract libraries or Soulmate. The name was gotten is it was named similar to Soulmate. So Soulmate was made by Transmissions 11. So kind of like same thing with Open Zeppelin, but very gas efficient. And there's also SolarD by Vectorized. That's also gas efficient too. So they are all contract libraries. Some are cheaper than the other. And next is SecP226K1 LUT Curve library in Huff. So I made this one myself. Yeah, so it's just basically a cryptography library I wrote in Huff. So originally it was implemented by Chronicle Labs in Solidity, and then I implemented it in Huff, and it's way cheaper than the Solidity version because I'm directly writing the bytecode myself. And then there's Uniswap v2 of okay, it's not here. Let me just copy it. So Uniswap v2 of was made by my friend and colleague Michael. So Uniswap v2 Huff is Uniswap contracts in Huff. So if you've interacted with Uniswap before, so the Uniswap ERC20, Uniswap v2 pair, and the libraries, Reentrancy Guard, UQ122, 112 thanks 112 for math stuff, math, and ERC20, Uniswap v2 pair Huff. So basically Uniswap Huff. And finally, Zyklon. So this one was made by me, Michael, and Samuel, both are my friends and colleagues too. So for a recent Huff hackathon or Huffathon, and so it's basically a transaction mixer, and we got second place. Yeah. So it's a transaction token mixer, just like Tornado Cash. If you've ever heard of Tornado Cash, that although hackers tend to like abuse it, but it was originally made for like privacy. So you can put in your token or funds in the Tornado Cash pool and then withdraw it with another address after passing some commitment and stuff. So it's just basically for private transactions. So we implemented it in Huff, and we had like a lot of gas difference. So creation code size. So creation code is when you are deploying your contract. There's this something thing called creation code. So Tornado Cash had 5,438 bytes creation code size, but with Huff, we had only 1,932 bytes. So that's a huge difference. And then the gas cost for deploying Tornado Cash was 3.4 million. Ours was just like over 400K. So very cheap, very cheap. Like compared to, it was not even up to 500K or 1 million, but this is 3 million, 3.4. So the 449,000 is even way higher than our own. So almost 3, 4 times or so. And our runtime code size. So runtime code size is after your smart contract has been deployed, the creation code will be like the creation code deploys the runtime code, and this runtime code is what exists on the blockchain, and that's what gets interacted with when you call. So full benchmark for function. Tornado Cash has this deposit and withdraw function. So as ours. So Tornado Cash own is about, I think, 10,883,000 feet. Or so I'm not sure I'm getting the number well, but ours was way cheaper, way cheaper, like way cheaper. So is our withdraw. Although there's no more difference here, but it's also cheaper. So yeah, that's to show you, although we had like some other stuff that made it cheaper and based on our circuit and the rest, but the Huff contract based on this one, we can see like there's a lot of gas difference both in code size and the gas consumption. So this is like some cool stuff with Huff. There are also numerous stuff with Huff that you can find in the Huff documentation. If you go to like Huff by example or stuff. So yeah, so what are some resources to get you started with Huff? So having seen this intro and you're like, oh, I want to get started with Huff, or I want to learn. So one of the best places to start is the documentation. I'm going to share this slide with anybody who needs it. So you can just message me on Twitter or my mail, which I'll show at the end of this slide. And then I'll just forward it to you or give you a link. Or I think I can share it in this chat. So yeah, I'll share it to this chat or instead copy it here. So if you want to get access to the slide, so the documentation is one place you should visit first. And eh, also in the documentation, if you are not familiar with how the EVM, that's the Ethereum virtual machine, works, you can go to docs.off.sh/tutorial/EVM basics. So there's a basic intro to how the EVM works, like concept of stack memory. And also just to note, my code here does not follow the Huff style guide, although this one does. This one does. Yeah, this one does. But this one in image does not follow. So the Hub style guide is just a way, like some set of rules when you are implementing your Hub contract that you should follow. It's not mandatory, but it's important. It's quite is useful. So like how you should declare your functions, how you should arrange your macros, how you should declare your variables, like basically all the stuff. So Huff style guide. So you can go to docs.huff.sh/style guide and overview slash overview. Then EVM.code is this site that I've been showing you guys for a list of opcode and like a list of Ethereum opcode, all of them. And you can also change your EVM version. Yeah. So Ethereum has been going through several upgrades over the time. Homestead was the first one some years ago. Then DAO was during the DAO hack, when Ethereum blockchain was forked and lead to like the other Ethereum version, the classic, I say Ethereum classic that people are not using that much. And then Tangerine Whistle, Spurious Dragon, Byzantium, Constantinople, Petersburg, Istanbul, and all of that up to Shanghai. Shanghai is the latest one. So each version has their own opcode. When I come to Homestead, I won't see some opcode here because they were not implemented at that time, and they might have like different gas costs. For instance, let me go to S load. See, S load has a minimum gas of 50. So before, S load was actually cheap. So it led to like some attack on the Ethereum blockchain. So they had to upgrade it. So this is showing 50 gas, and I think that was just it. It didn't have any warm or cold access. It was just 50 gas. It was quite cheap. But now is the same S load. If I search for it, a minimum that's for the warm access is 100, but the main gas is 2100. So it was increased. So if you go to EVM.code, you can select your EVM version, but always make sure you are in Shanghai so that you see the current implementation of the EVM opcodes and their real gas cost. And it also has like a playground where you can interact with EVM bytecode, which I'll use soon to show you guys something. So yeah, and also this tutorial is really awesome. So garden.meku plants and meku plants is name of the person who implemented the Sec256 K1 library that implemented in Huff. So originally he implemented it in Solidity for the company he worked for, Chronicle Labs, and then he implemented it in Huff. But he's also a Huffer. That's what we call people who write Huff. So yeah, he has this nice tutorial on getting started with Huff, so you can check it too. Yeah, and finally, um, rescues/Huff puzzle. So Huff puzzle is more like an interactive way to learn Huff by solving like some puzzles. It was made by my friend and I, Michael Amadi. He made a lot of contributions and like implementations, and I did some contributions to it. So it's a way to learn Huff, and we did it for the company I work for. So it's a way to learn Huff through solving puzzles, and I think it helped me too while I was doing. So you start with basic addition and go to basic bank, core value, core data length, create of um, distributor, blah blah blah, meter, full bar, and yeah. So it's just an interactive way for you to learn off by solving puzzles. So you can just look up this material or shoot a DM. Oh, and I didn't add it off. Actually has a Discord server where you can ask question. I forgot to put this in mine. So yeah, they have a Discord server. I'll just click on the link, copy the link, close it, then share it in our chat here. I say, okay, someone asked a question. No, I'll take questions soon. Yeah, just hold on a bit. So this is the Hub Discord server. if you would like to join, and you can ask questions. There are devs who are ready to answer you. I'm also there, so as several other persons who are ready to answer you with your questions. So good luck on your learning. And yeah, time for questions. So if you have any questions, you can ask. I'll just answer this one first. So as a developer, can you create or suggest an opcode for the EVM? Okay, actually you can. Yeah, what most people are not aware of is that Ethereum is not a private blockchain. It's not limited to just one person. You don't have, yeah, Vitalik was the one who made Ethereum. Not only him, but he started the whole movement with his co-founder, and is like one of the most popular guys behind Ethereum. But Ethereum is not a private blockchain, and you as a developer and a community member, you can contribute to the development of Ethereum. You can actually suggest your own opcode. You just have to be like you just have to suggest something that makes sense, right? If you want to add opcode, what's with the opcode do? How does it affect the network and smart contracts? Actually, there are tons of people who suggest opcode, and some of the opcode that you see here was not just made by the Ethereum co-founders. They were actually suggested by some persons. And right now, there are some EIPs that are trying to bring opcode to like the EVM. So I think EIPs like EOF, so EVM object formatter. So they are trying to remodel the EVM and like make some changes, add so that the EVM will like try to improve the EVM, something like that. So it's going to bring some opcode, it's going to remove some opcode too. Then how do you see the future of Huff language compared to Solidity language in popularity or usage? So Huff is actually gaining popularity over the recent years, and to me is one of the best alternative in smart contract languages for EVM. Because why? Because it gives you like a lot of great control of your smart contract. Like you implement exactly what you want as long as you know how to do it. And that's like it's just basically you writing almost pure bytecode. So Huff has a really, really bright future, and the people behind Huff are actually like known in the community. So Aztec Protocol and other community members who try to push Huff, like Dev Tuligan, J Trilly, and some others. So yeah, Huff is not dying, it's not going away, to only get better. And to me, it's one of the best alternative languages out there. Although there are several others like Fay, I think one lips like language like that, Viper and the rest, but off has to be one of the best aside from Solidity. The only kind of like a downside to it is that it requires like good knowledge of DVM. Like it's not as easy as Solidity to learn Solidity. So you need to understand EVM at least to a level before you can write off because you're basically manipulating the stack, the memory yourself. So everything that the Solidity compiler does for you should be aware of it. You should know it. You should like know how to implement it in Huff before you can actually write like a full-fledged smart contract in Huff. So yeah, and one thing again is that loops is kind of like a hassle in Huff. Um, Unlike Solidity, like you just do for like use the for keyword like for loop or while loop, and then you get the job done. In Huff, there's no for loop, there's no while loop. You have to manually do the loop yourself. And there was a time I was trying to implement a loop in Huff, and then it was kind of like my first time, and I've been writing Huff, but it's not actually I've written loop, but it was just like a tiny loop or so. But I wanted to do something in this contract, And I sat down and I started thinking, how am I going to implement this loop? But in the end, I did it. So that's like one of the downsides of Huff, but it's not something that bad. Based on like the things you stand to gain, like the amount of gas you save in your smart contract. So is there any question again?
Okay, guys, been an engaging moment. Who is can you mute yourself? Who is that?
Someone is speaking.
Moses. All right, I think that's fine. Um, just thank you so much. You've really done so much justice, making it easier for us to grasp. Please feel free to share your questions. One of those, takeaway or something we'll be doing as a community is to like create the Huff community that's just like gets beginners. So let's start doing some stuff. So we already one of the language we'll be kickstarting 2024 is Huff Language. So Osinachi said, please can we get a link to the matter? Sure, no problem. On the WhatsApp group, no problem. Are you on the okay? I hope you joined the Telegram and the WhatsApp group. Just like we have the Foundry and had that in Solidity, what do we use Huff? Okay, I think this is fine coming to you. While you're preparing to answer that question, let me even ask you this question. What inspired you to choose Huff Language for today's workshop? So what set it apart from other programming language in the blockchain space? So we have two questions now. Why do we use Huff, and what inspired you? And what set it apart from other language in the blockchain space? Just
Okay. Yeah, I will just start with why do we use Huff? Okay, you said just like we have Foundry and Hardhat and Solidity, why do we use Huff? So first thing I'll say, Foundry and Hardhat are not programming languages, right? They are development tools. They help you in like deploying smart contract testing and like invariant testing. Although I don't think Hardhat supports invariant testing, but Foundry does, and all of that force testing. So they are basically development tools that aids you in smart contract development, but they are not smart contract languages. But Huff is a smart contract language. So that's why we have it. So one benefit or why we use it is because of gas optimization. That's like the key benefit of gas optimization. That's what I've been saying. And recall when I showed you the Zyclone that we did as the zero knowledge transaction mixer or Toxu mixer that we did, the amount of gas difference that we got and the length of bytes code that we got 5,400 bytes, 1,900, the one in Huff. This one is in Solidity. Then gas cost. So imagine paying 3.4 million gas for deploying a smart contract, and then probably on Ethereum, gas price is like $120. So for like Paraguay or something. So timesing that, that's going to be a huge amount for you to pay. But over to us, off is way cheaper. Way cheaper. Like way cheaper. So this is like the sole benefit of Huff gas. Help you saving gas as a smart contract developer. You can actually use Huff with um so this is to say enough after writing, we don't need to test using those tools. No, you have to test your Huff contract. In fact, Huff, you should test Huff more than anything because you are writing in pure byte code. So it's actually harder. Like it's actually harder to get what you want done. So unlike Solidity that you can easily read your Solidity code and just understand what it does, it's not the same Huff. And take a look at this Huff contracts, for instance. Um, see how ugly it looks like. Although the reason is like this because of the comments I added by the side. And you said, what are the dev tools? You can actually use Huff with Foundry. As a matter of fact, this repository I used Huff with Foundry. You can see foundry.toml here. So I have the test for it. I wrote my test in Solidity, and then I'm testing my Huff contract with Solidity. So Huff has this Huff integration. There's a way they did it. So they have a Huff deployer contract. If you look here, you see on line 14, you see Huff deployer. So Huff deployer is a contract that is in this Foundry Huff folder. So the guys behind Huff, they wrote it, and with the Huff deployer, you can pick a Huff contract like I did here. You just have to put the file name of the Huff contract, and then it will deploy it for you and store it in a Solidity variable, and you can start doing your test with that. So you can actually use Foundry with Huff. I'm not so sure about hard hats, but I think there should be hard hats Huff. But I haven't used it because I personally I don't like hard hats. I don't like JavaScript. So I usually avoid JavaScript stuff, even though I was a JavaScript developer at some point years back. So yeah, so there are dev tools that you can use, and more are still being developed currently. And yeah, talking about dev tools, um there are tools like Stack Pasta. I'll just show this because it was made by my friend and my colleague at work. So it's a tool for helping you track the stack through comments in Huff. So this is it, Stack Pasta. So when you start writing Huff, you can download it. It helps a lot. See, it automatically adds comments for you by design. The reason we add comments in Huff contracts is so that you don't get lost. Because by the time you're writing your contract in bytecode, sometimes it gets overwhelming and you might not be able to track what is happening because they are interacting with the EVM stack directly. So that's why we drop, like we add these comments. Almost every Huff contract you see, you will always see comments by the side. It's just to help them keep track of what is happening at that time. You don't have to do this in Solidity because it's high level. But in Huff, you're writing something that interacts directly with the EVM, so you have to do this. Else you might just get confused and all of that. So the next question, why I chose to do Huff for the workshop. Basically, I kind of like loved the language when I learned about it. So I just found it quite interesting because knowing the EVM so well is what separates you from like um normal Solidity developer. So and Huff is one way to show that you're actually good with the Ethereum virtual machine. You understand it very well. And Huff is also quite interesting. I'm a fan of computer science. I like computer science stuff. And stuffs like this. So Huff was just like a challenge for me to take on. At some point, I didn't know it. I didn't know how it worked, but as I pick it up and start learning about it, and I fell in love with it. And it has a growing community, and this is just one way to push in the Huff language into the ecosystem. So another question, as a newbie or novice in blockchain developing, can I start with the Huff language? Actually, at this point, I don't think I should be the one to tell you yes or no. If you can do it, then why not? If you can go ahead and break things, why not? You are free to. So usually people will tell you no because it's kind of hard. Although there are several prerequisites for before you get into Huff. Basically the EVM, you should be familiar with these opcodes, how they work, by reading this, and there are other tons of there are tons of video on YouTube that teaches like basics of EVM. So, but if you can look at stuff and you magically understand how everything works, then why not? It's fine. You see, there are times where people tell you before you learn Solidity, you have to be a programmer first. I usually say that too because most times people will try to like hit like roadblocks because they've not written any code before, and Solidity is like a static language, or kind of that. So, but there are also people who started straight with Solidity and they are doing very well. But at least you should be familiar with the EVM before you go into Huff. You should know Solidity because a lot of things from Solidity, Huff builds upon it and EVM too. So at least you should understand how smart contracts are created, how functions are being executed in the EVM, all this stuff before you go into Huff. Else, you might just make it very confusing and hard for yourself. Something like that. So when did I start using the Huff language? Oh, actually, I started this year. Yeah, I started this year. I started writing Huff this year. So not that long ago. So I just had to do like some extra study so that I could understand this stuff. But I started writing Huff this year. So any further questions? You're
Okay.
welcome, Chimaya.
Um,
No, no question.
question.
I'm not sure if there's enough time. I wanted to show something else, but seems
Okay,
1:48.
let me see. Let me see if we have Dubane on the call. Right, Dubane time is supposed to be from 1:30.
Okay.
I think we just have to like do like a second session on that. If you're not okay, maybe later today or the new year, or what do you think? So we
Yeah,
don't keep the other speaker waiting for long.
yeah,
We're already like,
we can do that maybe New Year. And I wanted to explain how to like set state variable. Like this is like a more functioning contract than the other one. And this is it implemented in Solidity. And okay, probably I can there's no time, but maybe by next year we can go into it. But just to show you the amount of gas saving that Huff brings to the table, this contract is a store contract that sets this number, updates it, and then another function to retrieve it in Solidity. So it's kind of it's basic. When I compile it, this is the runtime bytecode of the smart contract, but this is the Huff version, the runtime bytecode. So are you seeing the difference? Very, very small. So because of it's so small, it's achieved exactly the same thing, but the difference is way, way much. Very, very small. This means it's very, 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 very cheap to execute than this one. Should be like 5 times cheaper than this one. Very small. This is like I had to like break it down, but it's a long bytecode. And this one, you can just see how small it is. Like very small. Literally, I can just put it in one line here. Like very small. And it achieves the same thing. The same thing. So I wanted to do a demo, but there's no time on my hand. So I'll just stop here. And probably by the new year, we can have a session where I go through this one and explain it.
okay. All right. At this point, we want to thank you, Jesse, so much. So what we'll do is internally just create a half channel. So we'll continue the conversation, the learnings. So for our cohorts who are here, the beginners, so want to like, you know, expose you from the basic. You see how he started and he showed interest and look at where. So one thing about this whole thing is when you grab a technology protocol, it's about being consistent and then go deep dive in that protocols. And doing that takes you far. So we don't encourage, jumping from one protocol to the other. So thank you so much. And we're already having one of our special, my friend, my brother, one of the African lead for the graph. He has been on the call for a while. I just want to thank you for your patience. And already like 20 minutes to his time, without uh, much ado. Do we continue on this or we'll I'm trying to like see how we could because we